which we convert the 10 symbols from 0 to 9 into 4 bits. So is this some kind of code we use? So we can convert from any of these 10 symbols to the BCD code and vice versa. Also, we spoke about gray code, and we mentioned this gray code is very important. Actually, we use it in error detection, and we mentioned why. When we compared between binary in sequence and the corresponding gray code in sequence, we found when we move from any state to the next state in gray code, we have only one transition. However, in binary, when we do the same thing, we found that sometimes when we move from one state to the next state, like we have two changes or 3 changes. Of course, if we move from one to another and we know we have only one change, so as a concept, does this make it easier for detecting error? Then we spoke about ASCII code, and we did examples for that. And also we spoke about parity check as a tool for error detection. This parity check does not fix the error. It just say we have error here. So that the receiver asks the transmitter to retransmit the message. We mentioned we have odd parity, we have even parity. So if it is odd parity and the receiver received even number of ones, so this means which should be odd numbers. So the message is wrong. There is error in the message. So ask the transmitter to retransmit the message. We mentioned this beside correcting the message by asking the transmitter to retransmit the message is not reliable, especially for satellite communication, because this means retransmission of messages in error. This will cause a long delay, and this is not accepted in satellite communication. So this is one disadvantage. The other disadvantage we mentioned, who remember, we have another disadvantage in this technique. Who remember?
It can't detect more than one error sometimes.
Can detect more than one error? I know what you try to say, but is there better statement than this? What's your code, by the way?
31.
Riley?
Yes. Would it be that it can't detect more than one bit flip within the?
Okay, who else can say here?
It can't detect an even number of errors, only odd.
Exactly. What's your code?
Code 30.
3?
30.
30. James?
Yeah.
Okay. Yeah, if we have double errors in the message, so like the examples we did, if like we have odd parity and we have double errors, like we have 1101010, for example. If we have double errors like 10000, so there are 2 errors. 2 ones change it to zeros. So we still have odd parity. but the message is wrong. So if we have double errors, we can't detect the error. So this is another disadvantage. So we mentioned there are other techniques like forward error correction, using a technique called the Hamming distance, but this like more communication than, but we focus on digital or fundamental of computer engineering. So we don't go far away in communication. But the idea here for gray code, for parity check, is a tool, simple tool. Of course, very simple, not complicated like other techniques, but we have this disadvantage, unfortunately. Okay. Any questions so far? Any questions?
Sarah, can you quickly explain again why parity method doesn't work with satellites very well?
This code?
Yeah.
Because as we mentioned, as we mentioned, you know, asking the transmitter to retransmit the message, and we know the data we receive it in frames, right? So retransmitting many frames in error, this causes delay. And in satellite communication, we already have long delay already. So we add more delays for this, relatively. When we talk about the delay, we talk about microseconds, you know, or nanoseconds even. But this in communication and like using voice or conferencing, this affect badly on reconstruction the original signal as a receiver. So that's why. Okay.
Okay.
Is that called latency? Is that what that is?
Latency, yeah, exactly. Okay. Okay, David, are you okay, David?
Sorry, Professor, you were late.
Okay. Okay, any other questions, please? Okay, now we talk about Boolean algebra and more logic gates. Previously, we spoke about three main operations, logic operations. So we spoke about three major logic gates. We spoke about OR, not OR, and AND gates. So now we'll talk about all gates, and also we'll talk about Boolean algebra. In our regular math, which we deal with analog numbers, analog quantities, analog signals, so we deal with regular algebra. But because here we deal only with two numbers, 0 or 1, so definitely we need another or different algebra to handle this topic. So this algebra is called the Boolean algebra. And we will study here the main properties of Boolean algebra to see the difference and how we use it to simplify logic expressions. We'll talk about this. So logic addition, this is also called the Boolean addition because it is logic addition. And we mentioned this happens when we use OR gate. So we have inputs, we have out. So how we handle the inputs for this gate? OR gate, we mentioned OR gate, the function of the OR gate is logic addition or Boolean addition. So we mentioned if 0 plus 0 is 0, 0 plus 1 is what? 1 plus 0 is 1. 1 plus 1 is 1. And this is called the truth table. Truth table is a table, gives us the relationship between the inputs and the output of this component, or this gate, or this subsystem, digital subsystem, or digital system. And we will see how we can put design for the circuit if we are given the truth table, or if we have a system, how we get the truth table. We'll talk about this. So previously, some of your friends mentioned, when we look at the truth table here, we can see that all outputs are ones for the different combinations, except the case if the two inputs are zeros. Like you see, everyone sees the slide?
I don't see the slide.
No, the slide's not up.
You don't see it? I'm sorry. Okay. You see it now?
Yes.
Yeah.
So based on the truth table here, this is the different combinations. We have two inputs, so 2 to the power 2 is 4. So we have 4 different combinations. You can arrange like you put AB, this is the output Y, you put 0, 1, 0, 1, then double the zeros and double the ones. So this versus 0 here is double, this one is double, so we got the 4 combinations. So in this box here, you can see this is the only case where we have 0 as the output when the two inputs A and B are 0. So this is very useful. This is very useful if we need to look at the timing diagrams. Timing diagrams means we see the waveforms of the inputs and the out. So timing, if you have been asked about draw the timing diagram or what is the timing diagram, this means you need to draw the waveforms of the input, of the inputs and the out. So if the input A is this stream of bits, 0, 0, 0, 1, 0, 0, this is the input A. The input B at the same time is 1, 0, 1, 1, 0, 1 simultaneously. So what is the output stream? What is the output Y? If we have inputs are stream of bits, so definitely the output will be the corresponding, or as the output, we will get the corresponding stream for these inputs. So one may go very traditionally, like 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 1. Is right, but this is not reliable. Why? Because if you have long stream, so it's you lose a lot of time to do that, and you may have more errors. So what we do, we use this advantage. The output is 0 if the two inputs are 0 at the same time, of course. We have transition here. We are very careful about the transition, like transition from 0 to 0 or 1 to 0 or 0 to 1. So we look at where both inputs are 0. And within this time interval, the output will be 0. Like what? Like, look at here. We have 0 here at A, we have 0 at B, within this time duration here. So the output within this time duration is 0. Look at again where both of them are zeros here. We have 0 and 0, so the output in this time duration is 0. Do we have any other zeros for A and B at the same time? Do we have?
No.
No. Perfect. What's your code?
7.
Even you just say no. Okay.
Thank you.
What's your code?
7.
7. Thank you. Same people. Please, we need more people. We need more people to participate, please. Yeah, it's increasing, but not too much. Okay. Still the same people are the dominant people. Okay. So yeah, there is no. So this means the output have zeros at only these two intervals. Then without looking for the others, just the rest is are ones. The rest are ones. So we have 0 here, and 0 here. So before is 1, and after are ones until we reach here, and then 1. So we figure out the time duration where the output is 0 based on the two inputs simultaneously, of course, are 0. Then automatically by default, the rest just put ones. Everyone sees this?
I'm following.
Okay, anyone,
Yes, yeah.
please, if you have question, ask before we move to the next step. And the gate. And the gate we mentioned for AND gate, the function of AND gate in general, logic multiplication. So the two inputs are multiplied to get the out. So if we have the inputs A and B, the output is AB for this AND gate. So again, the 4 combination of the inputs. Why 4 combinations? Why just 4 at the input? Why not 8, for example, or 16? Why just 4?
Because it's what, 2 power 2?
What is that?
You said it's only 4 inputs, which is 2 power 2.
2 power 2, exactly. What's your code say?
18, I think.
18. Travis?
That's me.
Okay, perfect. Thank you. Yeah, we mentioned we have 2 inputs, 2 bits at the input. So the combination is 2 to the power 2. Why 2? Because we deal with 0 and 1. So just 2 numbers. To the power 2. Why the power is 2? Because we have 2 bits A and B. So it's 4. Total combinations are 4. So 0, 1, 0, 1, 0, 0, 1, 1. So we have 0, 0, 1, 0, 0, 1, 1, 1. This is all combinations based on the truth table. But you can create the truth table. From the gate here, I give you the gate, you can draw the truth table. You can put the different combinations here based on the 2 inputs, and then the output is the multiplication, logic multiplication. So based on the function 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, because multiplication, 1 times 1 is 1. So again, if we look at the truth table here, we can see very remarkable state. What is this one? What is this state, you think?
When both inputs are 1.
Exactly. What happens when both inputs are ones?
You get 1.
Give 1. What's your code?
31.
Thank you. Exactly. If you look at the truth table here, the output is 1 only and if only. The 2 inputs are ones. The output is 1 if and only if the 2 inputs are ones. Other than this, for all other combinations, the output is 0. Because we mentioned this multiplication. So when you multiply 1 by 0 is 0, or 0 by 1 is 0. So the only one if both of them are ones. So the output is 1. So this is good advantage again if we have stream of inputs. So again, for the same stream of inputs A and B, what is Y for the AND gate? So what we do, like we did last time, what we do in this case? Who can tell?
There's only one bit that,
Can you speak
Yes.
loudly, please, little bit?
sorry, there's only one bit
So,
with this
so
and that is gonna be 1. There's, all the rest are 0. So it'd be the 4th bit
okay, so what's
from
code?
the,
What's your
from the
code?
right. It's 18, sorry.
What is your code number?
18,
13,
18,
1,
1, 8.
118. Okay. Okay,
Yeah.
thank you. Travis?
hmm
Travis, right?
Yes, that's correct.
Okay. Thank you. So what Travis mentioned, we look at the two inputs where both inputs are ones. Here, the two A is 1 here and B is 1. Do we have any other situation we have A and B, both of them are ones? No, this is the only one. So this means within this time duration and the output is 1. The output is 1 within only this time duration. And the rest are zeros automatically. I mean by default. The rest will be zeros because the multiplication will give zeros. So the only one here and both of the two inputs are ones. So this is, I didn't repeat drawing the inputs here because we have it here already. So I just draw the output for this AND gate based on these two inputs. Everyone sees this?
Yep.
Good. Now let us look at the properties of the Boolean algebra. Boolean is the name of the one who put these theorems. So just one, like you and me and like anyone, create this math structure. So you see how people works. So I need every one of you try to do something like this. So A plus 0 equal to what? And it's simple, but you know, create theorems. Simplicity is good. A plus 0, what do you expect for A plus 0? Equal A or 0?
A.
A, of course. If A is 1, remember we A, X, Y, whatever is just only 0 or 1. So if A is 1 plus 0, it is 1. If A is 0 plus 0, it is 0. So it is A plus 0 is A. Or of course, or X plus 0 is X. You can use any variable you want to express the bits. A, B, C, X, Y, Z, whatever you want. Just the variables represent the logic. Logic high or logic low, bit 1 or bit 0. A plus 1, what do you expect for A plus 1? What do we get? 1 or A?
1.
1. Why? Because if A is 0 plus 1, it will be 1. If A is 1 plus 1, it will be 1. So always, when we add 0, we will get A. Or when we add 1, we get 1, not A.
Professor,
Yes, go ahead.
if A is 1, then we get 1 plus 1. Shouldn't that be 0, 1 instead of just 1?
Okay.
That's, or saying logic addition.
Yeah, we mentioned we deal here with logic addition, not binary addition.
Oh, okay.
Binary addition is arithmetic, like a math, regular math.
Mm.
Okay, but here is logic addition.
Okay.
Of course, if you add 1 plus 1 as binary addition, so this 0 is carry 1.
Yes. Okay. Thank you.
But yeah, but this is logic addition, so it is 1.
Okay.
A multiplied by 0 is 0. A multiplied by 1 is A. A plus A is A, right? So if you add 1 plus 1 is 1, or 0 plus 0 is 0. So this is important here. A plus A is A. Means what? Means if you have in the Boolean expression, the output, if you have repetition or if you have a term repeated, so you just take or consider one term and skip the other terms. So like if A plus A plus A plus A, whatever the length of this repetition, all of this just equal A. What is the importance of this? What do you think?
These are the basic rules of Boolean algebra.
Okay, perfect. Basic rule. But yeah, that's true. But what is the benefit of this?
Well, this mimics like hardware, like actual
How
electronics.
yeah, perfect. How is
It's
this
like
reflected in the hardware?
AND gate, right?
Hmm?
It's like an AND gate, right?
Yeah, but how is this reflected on the hardware? You are close. What's your code?
3, I think.
What is your code?
3.
3? Okay, Joshua.
Yeah.
Thank you, sir. Yeah. We use these. Okay. All these properties serve for the design. How? When we are given a task to design this digital whatever, okay? So first of all, you need to use minimum number of gates in this design, or of course, or minimum number of ICs. Minimum number of gates. And we will see examples for like you have logic function, terms added and many terms. And when you simplify this expression using these properties, you will see like the output just connected directly to the input. Just wire, despite the expression gives you a lot of gates and or to reach to the output with the same result. But when you simplify this, like look, oh, I have repetition here, so skip the repeated. I have, as we will see, other properties. So when you simplify the expression, you may discover that it's just a wire.
Oh, Professor.
The connection between the input and the output is just a wire. Okay, so when he mentioned hardware, yes, this will simplify the design of the hardware. If I can do design with like a cost, for example, $10, why I pay $50? Okay, everyone look at how to save money and satisfy the maximum benefit, right? With minimum payment. So this just a little example for how what is the benefit of that. Yes, sir. Do you have question? Anyone has question? Okay. So A plus A is A. A plus A inverted is 1. A plus A inverted. The same A but inverted. Like what? Like 1 plus 0. 0 is the invert of 1. 1 plus 0 is what? Is 1. 0 plus 1 is what? Is 1. So A plus A inverted is always 1. A multiplied by A is A. A multiplied by A inverted is 0. A multiplied by A like 1 by 1 is 1. 0 by 0 is 0. A multiplied by A inverted, like 1 multiplied by 0, 0. 0 multiplied by 1 is 0. A double inverted, this is double inverted. You see this symbol here? Everyone sees this double inversion here?
Yeah.
So this means we go back to the original bit. So if A is 1, so 1 inverted to 0, and then inverted again, so 1 inverted to 0, then 0 inverted to 1, so we reach to the same A or same 1. So double inversion means it's the same one. Now, look at these properties here. Please follow and focus. A plus AB equal just A. How does this happen? Look at it. A plus AB. Now we use the properties for what we mentioned to solve this. A plus AB equal to what? We can take A common. So A common multiplied by 1 plus B. So if you multiply A inside, you will get A times 1 is A, and then plus AB. So the same equation. But 1 plus B is what? 1 plus anything is 1. 1 plus any variable is 1. So A multiplied by 1 is A. So A plus AB is A. But A plus A inverted B is A plus B, as if this inverted not exist. How this happen? Look at here, A plus A inverted B. Now, based on the property here, can we put A in the form as A plus AB? Yeah, A plus AB is A, plus A inverted B. So this equal to A. Now, here we can take B common, multiplied by A plus A inverted. A plus A inverted is what? A plus A inverted is 1. So B multiplied by 1 is B. So is equal A plus B. So A plus A inverted B is A plus B. These properties are very helpful for simplification to reach to a very reliable design. I don't like to say optimum because this is very theoretical word, optimum, exact. These are theoretical words like infinity. So we may say more proper design. A inverted plus AB is A inverted plus B. How we got this? Again, A inverted plus AB. Can we put A inverted like A inverted plus A inverted B? This exactly like here. If A plus AB equal A, so A inverted plus A inverted B is A inverted. Because we take A inverted common, open bracket, 1 plus B, which is 1, so A inverted times 1 is A inverted. So we can put A inverted here as in this form, plus AB. So again, look at here, we can take B common, multiplied by A inverted plus A, which is 1. B times 1 is B, so this equal to A inverted plus B. So A inverted plus AB is A inverted plus B. But A plus A inverted B is A plus B. Okay. Now, say if we are given the Boolean expression or Boolean function, y, the output is called either Boolean function or Boolean expression. It's the same thing. Can we draw the circuit from this Boolean function? Yes, we can. Just to put the output here. Start with the output and go back. Go back step by step until you reach to the inputs. So we put the output here. And now the two terms are added here. This one term, A, plus the other term is A inverted B. And the between them is logic addition here, plus. So this means if we consider this one input and this is the other input, so they both applied to OR gate. OR gate. This is called sum of products. We'll talk about this in details. And always, if the output is sum of products, so the output gate used is OR gate, because OR gives us logic addition between the terms. Between this term and this term, we have logic addition, not multiplication. Logic addition. So definitely this gate here we draw is the OR gate. Now this OR gate has two inputs because we have two terms here. One input is A and the other input is A inverted B. Perfect. A, this is just the input. I mean, this is the minimum input we can get, only one variable. But A inverted B, when we look at A inverted B, and the operator between A inverted and B is multiplication, because this A inverted B means A inverted multiplied by B. So what do you think? This is the output of what? If we have logic multiplication. So output of what? AND gate, OR gate, or inverter?
And gate
AND gate. Perfect. What's it called, man?
number 1.
Number 1. Perfect. Thank you. So we have new. What's this? Thank you. So AND gate, of course, right? So this AND gate has two inputs. One input is A inverted. It's very systematic, you know. I mean, it solves itself by itself. I mean, it's easy. And the other input is B. Now B is the minimum variable we can get. Now look at A inverted. When we have A inverted, this means this came from where? What is the gate connected here before A inverted?
A NOT gate?
Not gate, perfect, or inverter. What's your code, man?
20.
20. Great. Oh, Emily, thank you. Okay, Emily have good participation. Thank you.
Thank
So
you.
this means, so okay. So A inverted means this came from inverter. And the input applied to the inverter is A. And this is the minimum variable we can reach. So you see here, we reach it to like A input and B input. So this some sort of design. If we are given, if we have the, or if we are given the Boolean expression, we can draw the circuit. We can draw the circuit, and then we can, we may do simulation to check the circuit, and then we create the prototype for this function. Okay, so this is just a simple example for if we have the Boolean expression, how we get the circuit. So again, we start with the output, and then we go back step by step until we reach the original inputs, like A, B, C. Okay? Is this clear? Any question, please? Please, if you have question, ask. Then there are like some laws, commutative law, like A plus B equal B plus A. It doesn't make difference. If you add A plus B, if you add A first and then B, it's the same as if you add B first plus A. or A times B, this we talk about logic addition or logic multiplication. So A times B equal B times A. Associative law, like A plus B plus C, you see B plus C, we put it in bracket. So what this means for your imagination? When we put A plus like B plus C in bracket, what does this mean?
Is this like a triple or?
You mean just like one input. If A is just like one input, and the B plus C is one package as another input.
Like we have to do with this one first?
What is that?
We have to do B plus C first?
Yeah, this can be exactly like if we A plus B, if we add A plus B as one package plus C. So like here we have two inputs. One input is A, the other input is B plus C. This equivalent to one input A plus B, and the other input is C. Also, A multiplied by B times C is exactly equivalent to A multiplied by B multiplied by C. Distributive law, as you see, A multiplied by B plus C. So just multiply A inside, so AB plus AC. De Morgan's theorem. De Morgan's theorem. All these formulas used for, as we mentioned, to simplify the circuit of your design to save money and save time. Because if you have more gates for something, you can reduce it, so you spend more money. If you have more gates, of course, these circuits needs maintenance and troubleshooting. So if you have less number of gates in your design, this saves time for discover errors or maintenance, do maintenance. Now De Morgan's theorem. This is important theorem. What is this theorem? AB inverted. And please, AB total inverted is different than A inverted, B inverted. I always say this. I always repeat this, and unfortunately, at the end, I see some students also do this mistake. A, B inverted does not equal A inverted, B inverted. Does not. It's completely different. Please keep this in mind. AB total inverted like what? For example, if A is 1 and B is 0. If A is 1 and B is 0. So AB inverted means you multiply A times B, which is 0, then take the invert, which is 1. This differs than, so we have 1 here, okay? Same example we mentioned. A is 1 and B is 0. A is 1, so A inverted is 0. B is 1, so B inverted is 0. So we have 0 here. So this never equal to this. Okay. So what's this equal to? A, B inverted equal to what? Based on De Morgan's theorem, you see we have a bar here cover both A and B because this A, B inverted. So just for simplifying the theorem, just cut the bar in the middle. So a portion goes to A and the other portion goes to B. And invert the type of operation in between. So like here we have A multiplied by B. So we invert the multiplication to addition. So it will be A inverted plus B inverted. So first of all, we cut the bar to two parts, equal parts. So one part equal to A, so we put A inverted and leave the space and put B inverted. Then the operator between A and B is multiplication, it changes to addition. Simple. The same here. So you see here, B inverted is not equal to A inverted, B inverted. It's actually A inverted plus B inverted. Again, if we have A plus B inverted, so this inverted for total A plus B. So you should add A plus B first and then take the invert. Based on De Morgan's theorem, cut the bar in the middle here. So you have A inverted and B inverted, and then you change the type of operation here. So like we have addition, it will be multiplication. So will be A inverted, B inverted. But this for A plus B inverted, not for A multiplied B inverted. Okay? Everyone see De Morgan's theorem?
Yep.
Any question, please? Again, if you focus with me, you will not take much time at home to review this. It will be easy and better understanding, of course. But if you are busy with something else, and of course I don't see you, so this is up to you. Okay? Examples. X times X, X inverted plus Y. As I mentioned before, A inverted like this, we can't type it using the board. So, but we can type this. A inverted like this. So they are okay, the same. So X multiplied by X inverted plus Y. So based on the properties we mentioned, we can say this equal to X inverted plus XY. X inverted is 0 based on the properties we mentioned. A inverted is 0. So X inverted is 0 plus XY. So this equal to XY. So you see the expression, how the expression is simplified here. So if we look quickly at this, so this like X inverted plus Y, so we have OR gate for this, then to get this, and then we have AND gate to get the whole thing. But here just one gate, AND gate only, with inputs X and Y. X plus X inverted Y. Again, we mentioned this like A plus A inverted B. And we mentioned like ignore X inverted here. Not ignore, of course, like just to get the output, the result here. As if you ignore the X inverted, so it is X plus Y. And we proved it before. We can put X as X plus XY is the same as X. The whole thing here is X plus X inverted Y. So now, we just put this in another form. We didn't change anything. We just try to put it in another form, which leads to more simplification. But we didn't change anything. Because if you have X plus X equal to Y, for example, this is the equation. If you change something on the left side, you must do the same thing on the right side to keep the equation as it is. But if you change one side, somehow you add another parameter or subtract or multiply, and you didn't do the same thing for the other side, the equation becomes wrong. And definitely the final solution will be wrong. So here, when we put x in this form, x plus xy is the same. This actually equal to x, like as we mentioned in the properties. A plus A, we can put A equal A plus AB. So this x plus xy. But the purpose to do that, as we mentioned, to simplify the expression. Because when we put this and we add x inverted y, now we can take y common. So it will be multiplied by x plus x inverted. And we know this term is 1. So y times 1 is 1. So this is equal to x plus y. X plus y multiplied by x plus y inverted, multiply each variable into each bracket with every variable inside. So x plus xy inverted plus yx plus yy inverted. Yy inverted immediately is 0. Xx is x, so we have x here, plus xy inverted plus yx. Now look at here, we can take x common, multiplied by y inverted plus y. Any variable plus this variable invert is 1. So y plus y inverted is 1. So x times 1 is x. And x plus x is x. So you see here, this like the output, this equal to the output, whatever say f, the output f, or big Y. So this is the output. The output is x plus y multiplied by x plus y inverted. So if we look at to get this output, and you have input x and y, so you have gates in between from the input to reach to the output. We have gates, we have inverter, we have OR gate, then we have AND gate. But after simplification, what happens? This f equal to what? Equal to x. So what this means? What is the connection here between the output and the x? It's just a wire. So if this say if this is f here, say this is f. So at the end, this means f, the output, equal to x. So what is the connection here? It's just a wire. So you have f here as output. And then based on the original expression here, you have gates here until you reach to x and y as inputs. But in fact, after simplification, this f is just connected directly to the input x. One may ask, oh, so what is the function of y here? We have another input. How does this input disappear? It's not disappear. It's actually, it doesn't matter. Sometimes, as we will see later, you have certain inputs at the input of the system. They don't have effect. They came from other stages before, but they don't have effect on the function of the last component. They don't have effect. So this component or this input is called, it doesn't matter. If you take it 1, the same result. If you take it 0, the same result. So why here, it doesn't matter. Has no effect on the output. So just for the people who think, oh, how this happened? We have another input here. So how it disappeared here? Of course, it disappeared based on the analysis. But what this means? This means this Y input, it doesn't matter. Okay? It doesn't have effect on the output. Okay, now, do you like to take like 10 minutes break or we go ahead, and if we finish little early, we can leave. It's up to you.
I think I'm good to keep going.
Continue or take break.
Yeah, I would continue as well.
Continue.
I'd
Okay,
continue.
you agree, guys?
Yeah.
Okay. So sum of products 4. This output function or Boolean function, it may take a form. It's called the sum of product or SOP, like this, like sum of product. So we have products here, product term here. We can see A multiplied by B, C multiplied by D. So these are product terms. And these terms these terms added, logic addition. So we have plus here, sum. So this is called the sum of products. And this one is actually the most popular one used to express the Boolean function. There is another form, it's called the product of sum. So like here, if you look at here, we have A plus B, and we have C plus B. This one term, C plus D, another term, and then they multiply. So it's called product of sum. This is another format for Y expression or Boolean expression, but as I mentioned, sum of product is more popular. So what do you think? The output gate we use here for this sum of product, what kind of the output gate we use here?
Or.
Or. Thank you, sir. So here we use OR gate at the output immediately. The last gate here is OR gate. So for Y here. And then whatever we have here as inputs. What do you think for product of sum? What is the kind of the last gate at the output?
And
Perfect. So here we have AND gate. Is this useful for the design? So we have AND gate logic multiplication. So this one term like A plus B, and this is the other term like C plus D. Here's the two inputs here, A inverted B, and the other one CD. Okay. Give me the code numbers, please. For the people respond. Your code numbers.
31.
31. Perfect. Next. I heard more than like 3 people. 15. Thank you. Another one? Just 2? Okay, thank you. But as I mentioned, we most likely we focus on sum of product. The other one is similar, just the only difference like what I mentioned here. Okay, so to save our time, dealing with like this sum of product, which is, as I mentioned, most used. So that's fine. So like this, Y equal ABC plus CDE plus, so we have product terms here and then sum of the product terms. So here like we have OR gate at the output with 3 inputs. Any logic expression can be changed into sum of product. Any logic expression you have, you can convert it to sum of product by applying Boolean algebra using the properties we mentioned for Boolean algebra. We can convert any form of Y or F, Boolean function, as sum of product. Like this one here, A multiplied by B plus CD. Definitely this is not sum of product. So we need to convert it to sum of product. So we multiply A times B, then plus ACD. So we have two terms, product terms, and they add. So this is sum of product. AB plus B times CD plus EF. So this form is combination of different things, but definitely not in the sum of product form. Sum of product form like we mentioned here, like this one here. But this something like a combination of different things. So it's simple, AB, then multiply B inside, so B is plus BCD plus BEF. Again, this one here. This definitely is not sum of product. So how we convert it? Immediately when we see this expression here, this means we can use De Morgan's theorem. So for the big bar here, the upper bar, we can cut it here. We can cut here to two bars. One part goes to A plus B, so A plus B double inverted, and C inverted. Then the operation here, we have plus, so we invert it to multiplication. We switch it to multiplication. Then A plus B double inverted, we mentioned before, A inverted is A, or A double inverted is A. It's the same, A plus B double inverted is A plus B, multiplied by C inverted. Then multiply, so you can multiply C inverted inside, so you have AC inverted plus BC inverted. Now this is sum of product form. Okay. Any question so far, please? Any question?
Is the general goal always to just simplify it as much as we can?
If we, this conversion from whatever you have, expression, whatever looks like, to sum of product. Sum of product form, like this one. So if you look at any expression here we converted is not sum of product, like this one is not. So now this is one, yes. This one is this one. And we'll know why we do that. Why we need to convert from different form, whatever the form we have, to sum of product. We mentioned we have two techniques we use for the design, either sum of product or product of sum. The most popular approach used is sum of product. So we focus on sum of product. So before we go deeply, we talk about how we convert any Boolean expression in another form, how we convert it to sum of product form. Okay, so we start with this first, and then we'll talk about the design. So the standard sum of product form, we have standard form. What is this form? A standard sum of product expression or form is the one in which all the variables in the domain appear in each product term. We mentioned this is called the product term. This is called the product term. So what is mentioned here? We have standard form for the sum of product. The standard form means each product term contains all variables used. Like if we look at here, for example, for this expression here, do we have all variables here in each term?
No.
No, perfect. What we miss here?
You're missing B on the first one.
B or B inverted, it doesn't matter. but we miss B. Whatever is B or B inverted. What we miss here?
You're missing A.
A, perfect. What's your code, please?
2.
2. Thank you. Exactly. So this, yeah, is product, is sum of product, but not standard form. Is some product form, but not standard. To get this standard, we must have here in this term somehow B or B inverted multiplied, and here we must have A or A inverted multiplied. We'll see how we convert from one form not standard to standard form. But now we focus on what is the standard form. Okay. So a standard sum of product expression is one in which all the variables in the domain is called, this is the whole thing called domain here, appear in each product term in the expression. All variables. A variable, either the variable or the variable inverted is it doesn't matter. Example. If you look at this expression here, is this a standard form or not?
Yes, it is.
Yes.
Yes. What you mentioned, Amy, you agree or not?
Yes, it is standard form.
Okay. Yeah, who said yes, please? Your code.
Me, 23.
23.
20.
Okay. Okay, Amy, thank you. Thank you both. Okay. So this is standard form. Why? If we look at any term, every term actually, we'll see all variables exist, like A, B, C, D. Yeah, we have B inverted, it doesn't matter, but B exists, either B or B inverted. A, B, C, D, A, B, C, D. So we have 4 variables here. The 4 variables exist in each term. So this is a standard form. Okay. What is this standard form important for us? I mean, why it is important? Standard sum of product expression are important in construction of the truth table. From this, we mentioned the truth table gives you the function of the component or the system. So to construct the truth table, we must have this form as standard form. Second, is important to draw Karnaugh map. Karnaugh map is graphical solution, and we'll see how this graphical solution is important in simplification the final form. Okay, so let us go step by step to avoid any confusion. So for the time being, this standard form is important for 2 things: to draw the truth table or construct the truth table, and to draw the Karnaugh map. So to do any one of them, this expression must be, we must have this expression in the standard form. Now, how we convert from non-standard form to standard form? We are given y, assume we are given y, the Boolean expression, y or f or whatever, but not standard. To go through the truth table or Karnaugh map, we have to convert it to standard form first. How we do that? Before we go through this point, we need to define the product term in sum of product format. What is the product term? We say here, this is a product term, right? Everyone follow?
Yeah.
Please focus with me to,
Yep.
to be clear for you. This is a product term. This is a product term. So a sum of product terms. So how we define the product term is here. Assume we have the variables A, B, C, D like 0, 1, 0, 1. Okay? Now, the product term of this is the term in which we multiply these variables, we get 1. So the value of this product term is 1, not 0. It's bit 1 always, bit 1. So how we get 1 from these variables here? If we multiply A, B, C, D, definitely we'll get 0, right? Because we have zeros. So to get 1, how the product term should be? A is 1, perfect. But B is 0, so we have to use B inverted to keep 1. C is 1, perfect. D is 0, so we have to use D inverted. So now when we use A, B inverted, C, D inverted, so all are ones. So the output is 1. So this is how we get the product term, or this is the meaning of the product term. The value of this product term is 1. So when we look at the product term, for example, here, so we have A, B inverted, C, D inverted. This means as inputs, A is 1, B is 0, because we use the B inverted here. C is 1, and the D is 0, the original variables. Okay? Now, how we convert from whatever non-standard form to standard form? Look at this expression, for example. Y equal AB inverted C plus A inverted B inverted plus ABC inverted D. Is this standard form?
No.
No. What's your code, sir?
7.
What's your code number?
7.
I don't hear you.
Oh, 7.
7. Shane. Okay, thank you, Shane.
I said no again, just to get it.
Yeah, okay. Thank you. Okay, guys. Please, everyone participate. Everyone participate, please. Okay? Okay. It's not. Why is not? Because look at what is the maximum number of variables here? This one, right? This one we can see we have A, B, C, D. Regardless C inverted or D inverted. So we have 4 variables here. So the maximum number of variables in this expression is 4. Look at how many variables here we have in A inverted, B inverted. Just 2, right? This means we missed 2 variables here. Here we have A, B inverted, C. So we missed one variable here. One variable which is D. Here 2 variables which is CD. So how we convert from this form to standard form? Let us take the first product term here. AB inverted C. Again, we try to put it in another form. So we use our knowledge and properties of Boolean algebra to reach to our goal. We need to reach here from non-standard form to standard form. So what is missed here? Variable D. Okay, so can we multiply this term by D plus D inverted? Can we do that without changing anything?
Yes.
Yes, of course.
Yes.
Why? Why yes?
Because
Because
D plus the inverted is 1.
One. But thank you, sir. What's your code?
2. But I think someone else answered the
Yeah,
first
what is the
part.
other one?
21.
So two, you mentioned two,
Yeah, 2.
and the other one,
21.
21. Oh, okay, thank you. Yeah, more people participate now. That's great. Thank you. Exactly. We just multiplied by D plus D inverted. We did it's the same equation here because we know D plus D inverted is just one. But again, we put it in this form to get standard form, to reach to a standard form. Now multiply A inverted B inverted C D plus A inverted AB inverted C D inverted. So now how many terms we have in each term, in how many variables in each product term? Huh? How many? How many variables here?
4.
4. So now we converted A, B inverted C to these two terms, which are standard form, in the standard form. Next one, A inverted, B inverted. So we have two variables missed here, C and D. So we take it step by step. So we consider one variable first, and then we consider the other one. So let us take C. So multiply, same thing, multiply by C plus C inverted. So we got A inverted, B inverted C plus A inverted, B inverted C. So it's better now, not perfect, but it's better because instead of two variables, now we have three variables. But we still have one missed, which is D. So take each term multiplied by D plus D inverted. So A inverted, B inverted C multiplied by D plus D inverted. Plus A inverted, B inverted C multiplied by D plus D inverted. And multiply again. Go inside. So A inverted, B inverted C D plus A inverted, B inverted C D inverted. And the same thing here. So now you see we converted A inverted, B inverted as two variables into four variables. So we converted to standard form. Now add these things, all of them, add what we got here. So A, B inverted C equal to this. So we put this here. Then plus A inverted, B inverted equal to this. So we add them up here. And the last term plus A, B, C inverted D. Okay. We should look at just one look for if we have any repeated. So this is right, okay, but more professional, just to look at the terms. If you have any repeated terms, just take one. So say we have a term repeated 2 times. So just one and skip the rest. The repeated ones. A term repeated 3 times. Like we mentioned, A plus A is A, or A plus A plus A is A. So just take one. But now we got the standard form. Another example here. Look at this example. Y equal A inverted B plus B inverted C plus ABC inverted. ABC. Okay. Is this a standard form? And why?
No, because you're missing a C term in the first product and a A term in the second.
How many variables we should use here in each term?
3 total.
How many?
3.
3. Perfect. What's your code, please?
2.
2.
Oh, I'm sorry. I'm 20.
Twin. Okay. Okay, Emily. Yeah. Thank you, Emily. Thank you. Everyone heard this? The maximum number of variables in one term is 3. This is the maximum number of variables. So this means each other term must be 3 variables. So we have here the first one, A inverted B, so we missed C. Second one, B inverted C, so we missed A. So we have doing the same thing we did before, so you can convert from A inverted B as 2 variables to 3 variables. How? We missed the C, so we multiplied by C plus C inverted. Second term, we missed the A, so we multiplied by A plus A inverted. The third one is perfect, so it is, we copy as it is. Then multiply, then add, so we got this. Now we have the standard sum of product form. Each term has the maximum number of variables, which is 3 for this case. Is this clear for everyone, please?
Yes.
Any questions here?
I have a question.
Yeah, go ahead.
Earlier, you told us a lot of rules, and I was wondering if we need to memorize all of the rules.
What is that?
Can you scroll up?
Scroll up, okay.
Yeah.
I think
Yes.
he's talking about like the domination identity
Yeah, those
associative, like those laws
Ye-
for Boolean algebra.
Okay, so what's your question? I scroll up. So what's your question?
Yeah, that was my question. Like you told us a lot of rules. Like A double inverted is A, A times A is A. Those kind of rules you told us, should we memorize them?
If it, I spoke generally here. If you have after when you get this or any other function, if you have any repeated terms, just use one of the repeated terms. So say A B inverted C D is repeated in the other terms 2 times. Whatever the number of times, you just use one and skip the repeated ones. Okay?
Okay.
Does this answer your question?
Yeah.
Okay, good. Now, all standard Boolean expression can be converted into truth table format. If we have this expression, we can get the truth table. All standard sum of product expression can be determined from the truth table. So like two-way propagation, two-way direction. Like from the Boolean expression, if it is standard, we can get the truth table. Or if we have the truth table, we can get the Boolean function. Example, now we have example here. Develop a truth table for the standard sum of product expression, this one. First of all, before we do anything, we look at this expression. Is this standard form or not?
It's in standard form.
Yes.
form.
So give me your code, please.
Number 10.
10. Perfect. Thank you, Arthur. Yes, is standard form. If it is not, before we do anything, we must convert it to standard form first. Okay, now, how we draw the truth table from this expression? Remember, each product term here has value bit 1, okay? Remember this. So we have 3 variables. First of all, how many variables do we have? 3 variables. So 3 variables means 2 to the power 3 is 8. So this means we have 8 different states or different combinations, different unique combinations. So we start with draw the truth table like this, put the inputs A, B, C, and then a column for product term, call it product term, or actually it's called also fundamental term, and the output Y. Okay, now we need to fill out this table for the inputs. we have 8 different combinations. So we start at the right side. We put A, B, C like this, in this, like this, or actually is more convenient, as we will see later. Start A from here, A, B, C, because this is useful for Karnaugh map also. But okay, this is okay because we don't need it now. So whatever you put it, A, B, C, or A, B, from right to the left or from left to the right, for now is okay. But you start 0, 1, 0, 1, 0, 1, 0, 1. This is 8. 1, 2, 3, 4, 5, 6, 7, 8. Then double the number, 0, double 0, then 1, double 1, then double 0, double 1. Then double zeros again. So 0, 0 is 0, 0, 0, 0, then 1, 1, 1, 1. So we got all different combinations, unique combination, is not repeated. If you look at any state, is unique, it's not repeated anywhere in this 8 combinations. And the simplest way to get that, as I mentioned, start with 0, 1, whatever you have here. Start with 0, 1 on the right side, 0, 1, 0, 1, 0, 1, and then double the number. Okay. Now we need to figure out these product terms. Where A inverted, B inverted, C. Where A inverted, B inverted, C, do you think? A inverted, B inverted means, as this product term, A is 0 or 1?
The product term is 1.
I'm talking about A, not A inverted. We know the multiplication here must give us 1. So when we have A inverted here, this means A, the original A, is 0 or 1?
1.
Man.
0.
0. Okay, let us go back here. Man, I'm joking with you. So, okay, let us go back here. When we got this product term, so what we use here, when A is 1, so this A is okay. But when B is 0, we use the B inverted. C is 1, is okay, so we multiply it by C. But when D is 0, we use the D inverted, because we need to keep this number 1. But the original bit here is 0. If we multiply by B, so this value will be 0. So it will not be the product term. The product term must be 1. Everyone sees this? Yes, no?
Yes.
Question?
Yes.
Okay. So the same thing here. When we fill out the truth table here, this is the first product term. A inverted, B inverted, C. This means the output in front of this product term, where we have A is 0, B is 0, C is 1. Where A is 0, B is 0. A is 0 and B is 0. So A 0, B 0. A 0, B 0. Okay, so either this one or this one. So what is the next one? C is 1. So A 0, B 0, C is 1. So this product term is here. So the output as this product term is 1, right? Okay. Now let us look at the other product. A, B inverted, C inverted. This means A is 1, B is 0, C is 0. So let us look at where B is 0 and C is 0. B is 0 and C is 0 is here. It's here. So what is the next one? A is 1, so it's here. So this one is A inverted, A, B inverted, C inverted. So as this product term here, which corresponding to these inputs, the output is 1. The output is either 0 or 1. So we figure out where is the output once. and the rest will be zeros. So you figure out the relationship between all inputs and the corresponding outputs. So you have complete truth table. Now let us look at the last one, ABC. This means A is 1, B is 1, C is 1. This most likely is the last one. So this is the product term in front of these inputs, where Y is 1. So we have 1 here, 1 here, 1 here, which represent the product terms. So the rest are zeros in front of the other inputs. They are zeros. So when you figure out the output and the all different combination of the input, so you get the truth table. Okay. Any question here? Any question, please? If you have question, ask me. Don't hesitate, please. As we mentioned, we're all here to learn.
Professor, I have a question.
Yeah, go ahead, please.
Yeah, so
Can you speak loudly?
on the product term in the truth table, there is a column that says product term.
Product term, yeah.
Can you explain to me why are they in the position they are? Especially the last term ABC that is at the last row.
This one?
Yeah.
Okay. The product term here is taken from the expression here, okay? So we need to determine where these product terms lies in this truth table. Because as these product terms, only as these product terms, the output is 1. Other than this, the output is 0. So we put a column here for product term, and now we search for where this product term, A inverted, B inverted, C. How we know where is it? As I mentioned, this product term means A is 0, B is 0, C is 1. So we look at where A and B, both of them are zeros. They are zeros here. They are zeros here also. Yeah. So either this one or this one. Which one of them? Look at the other variable, C. C is 1. So 0, 0, 0. So this is not. But here, C 0, 0, 1. So it is this one here. So now the output as this product term is 1. We need to look at where Y is 1. Y is 1 is based on the product term. If you figure out where is the product term, and of course, it's easy to figure it out, as we did, based on the inputs. So you determine the output is 1. Okay?
Okay.
Does this answer your question, Chen?
It does. And one more question. One more quick
Yeah,
question.
sure. Go ahead. Go
You
ahead.
also said that we double the number, double A to find B, and we double B to find C. Is that-
Double A, what you mean by double A?
So you're saying that in order to find the value of B or C, we have to double a number before it.
No, I look at just the input. Again, let us look at this. A, B inverted, C inverted. Where is the location of this product term in this table? Where? We have a column here for product term. So A, B inverted, C inverted, where? Is here or here or here or here? How we figure it out? Look at the term. A, B inverted, C inverted means what? Means A is 1 as an input, B is 0 as an input because we use B inverted here. C is 0 as the input because we use C inverted here. So we look at the location where A is 1, B is 0, C is 0. So B, C zeros are here. Do we have any B and C are zeros? No, just here. Either this one and this one. So the product term, this product term, either here or here. So how we know is here or here? Look at the other term. The term left is A is 1. So this means we are here. So this product term in front of these inputs here. Now the output Y equal to 1 based on this, which means in the circuit, in the design, whatever the design inside, but if we have the inputs, A is 1 and C is 0 and B is 0, the output of the system must be 1. You see what I'm saying?
Yeah, thank you, sir. I got it.
Yeah. Other inputs, the output is 0. Other than the product terms, the outputs are 0. The output is 1 only at the product terms. Okay?
Yep.
Any other question, please? Okay. Now, do we have, oh, okay. So, okay. So let us do this and we'll continue next time, okay? So determine the standard expression from a truth table using sum of product technique. Now we are given this truth table, vice versa now. Now we are given the truth table here. And we need from this truth table to get the function, the standard expression. Even if I didn't mention standard, it is known now that the output from this will be standard. So here we are given the expression and we got the truth table. In this example, we have the truth table and we need to get the expression. So this truth table is given as it is here, okay? And now we need to get Y as expression. So what do you think what we do? The first thing we do, these are the outputs. The Y is the output here. So of course we look at where Y is 1, because we mentioned as a product term Y is 1. So we have ones here. So put the ones in a circle, just to differentiate between ones and zeros. Just put it in a circle. All ones you see in Y, put it in a circle. And now look at the corresponding inputs. What we have, A is 0, B is 1, C is 1. So what is the product term should be? The first product term or fundamental term. Say F1. F1 like the first term here. Like this one here. The first product term. F2 like this one. F3 like this one. That's what I mean by F1, F2. So what is F1 here as a product term? Remember, we have 0 here, okay? So what do you think?
0.
No, we need the variables in terms of the variables. The product term is in terms of the variables, here. But what we should say here in front of this one, like we say ABC or something else. Is F1 equal ABC or something else?
A inverted BC.
Can you speak loudly, please, to allow your friends hear you?
A inverted BC.
Perfect. Thank you. What's your code?
7.
7. Now, why A inverted, not A? Why you use A inverted? And why you use the B, not B inverted?
Because each term
So
is
first of all,
A.
why you use A inverted?
Because at that row, A is 0.
Yes,
And
because
gate.
you see here, just to confirm with our friends. Because in front of this fundamental product, A is 0. We mentioned we can't use a 0 because the multiplication will be 0. But the multiplication must be 1. So we have to use A inverted. You use the B. Why you don't use B inverted?
Because they're already 1. They don't have to
It's
be
already 1. Perfect. Which we needed because the multiplication, we need the multiplication to be 1. If I use B inverted as I say, so this means B will be 0. So the product will be 0, not 1. So definitely we use B. We use B because B is 1 already. We use C because C is 1 already. We use A inverted because we have A as input is 0 here. So we use A inverted. Okay, thank you. The second one. Anyone tell me? So what is the product term here? Corresponding to this one.
A, not B, not C.
AB, not AB inverted, C inverted. A, B inverted, C inverted. Thank you. What's your code, sir?
31.
31. Perfect. Thank you. You see, B inverted, C inverted, because both B and C are 0. So we have, they should be 1 to get the product term 1. The third one, A, B, C inverted. The last one, F4, is already all of them are 1, so we just use ABC. Now Y is the sum of F1 plus F2. Remember, we say sum of product. Technique we use. So we add F1 plus F2 plus F3 plus F4, which is this expression here. Now this is the Boolean function we got based on the truth table we are given here. Okay, we'll stop here and because already 4:30, yeah. So we'll continue next time. But as I mentioned, for anyone came late, we have quiz next time. The class, we don't have class on June 19th because there no class at this based on the school. So the class after that will be on June 24th, next Tuesday, and we will have quiz 1. Quiz 1 will be a portion of the class. So we will continue what we left here, and then we'll take the quiz. The quiz covers notes 1 and 2 and 3. Very similar to the examples or what we discussed in these slides. You don't need to look at any other resources. Just focus for what we discussed together. That's why I always, your attendance is important. Because as you see, how many discussions we have and the questions, okay? Any question before you leave? Any question, please, before you leave?
Wait, sorry, can you repeat like the thing for the quiz again? Is it
The quiz on June 24th, and it covers everything except what we discussed today. We discussed today notes number 4. The
okay?
quiz is only 1 and 2 and 3. So today is not included in the quiz.
All right, so the quiz will be on the 24th in the beginning of class.
As I mentioned, we start with we'll continue what we left here, and then we'll take the quiz.
Okay, got it. Thank you.
Any other questions? If there is no question, yeah, go ahead. Go ahead, please.
No, I said no. No questions.
Okay. Okay, go ahead. Go ahead, please. If you have question. Okay. Okay, thank you, everyone. Have a good the rest of the day.
Thank you, Professor. Have a good day.
And see you next time.
Thank you,
Thank you,
Professor.
Professor.
Thank you. Bye. Take care. Take care, everyone.
Bye.
Bye.
Professor, I came late today. Did you fix that already?